Hello everybody, we will continue our lecture series in this optimal control guidance and estimation course. And last class we have seen some details about other things, but this particular course, this particular class will start this constraint optimal control. Okay, so far we have not talked about this particular topic. So next couple of lectures we will see what differences it brings when you put constraints into action. And when I mean constraints, it means inequality constraints. So let us see first control inequality constraint, and towards the end of this series of lectures we will talk also about little bit about state constraint problems as well basically. Alright, so this is the outline of the topics that are lined up in this particular lecture. First thing is a little bit motivation about why we want to study again this constraint optimal control for problems. And as I told, lot of practical applications demand that we formulate the problem in this framework actually. A little bit brief summary of unconstrained optimal control, just to recapitulate certain derivation process and things like that. That will form the basis for constraint optimal control also basically. And then what we will study in detail this particular lecture is Pontryagin's minimum principle in some sort of a generic framework. Then probably this will be the topic of this particular lecture, but subsequently we will also study this time optimal control of LTI systems in detail, and especially this time optimal control of double integral system, which is a very standard textbook sort of problem, is kind of a benchmark problem nowadays actually. You will find this problem in many textbooks, and we will also cover this in fair detail, which will kind of clear our ideas what we are talking about here actually. That will be followed by fuel optimal control and as well as this energy optimal control. So, there are various practical problems which will demand this kind of control system analysis and synthesis basically. And towards the end of this couple of lectures, we will also talk a little bit on state constraint optimal control actually, and how do we solve or how do we propose solutions for incorporating these kind of constraints. Alright. So, let us get started, and this particular topic lecture as I told will contain these first three topics. Rest of the things we will study as we go along in next two lectures basically. Alright, a little bit motivation for why we want to study this topic. First of all, as we know, physical systems are always restricted by constraints on both control as well as state variables. That is the reality, we can't escape from that actually. So, let us see some few examples how it naturally pops up. So, first of all, suppose you think that okay, rockets are controlled by thrust deflection angle actually typically. So, either the engine is swiveled, the entire engine will be kind of swiveled in a little lateral directions. So, that if you have something like let us say if you have some rocket like this, okay, and you have something like a thrust coming out. So, this is the nozzle part of it. Now, if the nozzle is reflected like that or that, so then the thrust will be like this. Initially it was like this. Okay, but if the engine is if the nozzle is deflected, then the thrust will be like that. So, that means it will still have a component in the vertical direction, but also have a component in the horizontal direction, lateral direction. So, that particular component which will act here, and because CG is here, okay, it will act as something like a moment, and that is the mechanism for controlling the rockets actually. So, obviously, when you look at it, this engine or this nozzle deflection that you are talking, one of the mechanisms for thrust deflection cannot exceed beyond a certain limit, and typically the limit is also very small, and the limit is roughly about 10-15 degrees actually. So, if you talk about a problem which demands something like 35-40 degree of nozzle deflection, obviously that is meaningless, because we simply can't implement such a control strategy actually. And you can also think that okay, well, if the control is constrained, then the system may go unstable. Well, that may not be the case, because we are not talking about something like instantaneous effect and all that. The vehicle can still be stable, and then we want to have a course correction and things like that. And also remember, we have a long period of time to kind of take control action. In other words, even if the control saturates for some time, then eventually if it comes out of the saturation, then it's as good as a good problem basically. Okay. So, that is the whole idea of studying this control, I mean constraint control problems actually. Anyway, so that is one example. The other is let us say this suppose you talk about aircrafts now, not necessarily rockets. Then you also know that aircrafts are having this various control surface deflections, especially like elevator, ailerons and rudders and things like that, and we have discussed about that in flight dynamics lectures. So, even there the control surface deflections are typically limited to something like 30 degree, 40 degree and all that. And just to make your idea a little more clear, we are talking about control magnitude constraint here, but in general the control is also constrained in its rate actually. Even the magnitude may be small, if the rate of change is very high, then that also is not acceptable actually. Okay. So, these are the things that that kind of motivates, but we are not talking about rate of control constraints here. We are still we are still talking about control bounds. So, especially if you plot it, let us say if you plot the control variable, okay, u, and then we are just talking about something like a u max and then a u mean here actually. Okay. So, what I am talking is in practical reality it can still be bounded, but the chattering can be there, that means the rate can be very high, and that is also not acceptable. Okay. And if it is not chattering and then something happens like this and things like that, then also it is not acceptable, because of these regions are violating actually. We cannot I mean these are not acceptable controls actually. Okay. So, that is what we are interested in. We are interested in having something which will talk about some bound of u max and u mean, and the control solution will lie between this u max and u mean, okay, all the time, especially until t equal to T f actually. Yeah, that is what we are worried about. T f can be as good as infinity also basically. Yeah. Anyway, so this is the problem. These are the examples. Control surface reflections are also constrained by hard bounds. And then coming to the state constraints part of it, let us say aircrafts cannot climb beyond a certain altitude, okay, because if they keep on climb, then ultimately they will lose lift because of low dynamic pressure. As we know that lift and drag are typically very strong functions of dynamic pressure, L equal to half rho v square into S into CL, right, if you remember the formula. And it turns out this is the lift coefficient is CL and the surface area is S, but this part is something what is called a dynamic pressure. Now, it turns out that rho is not a constant number, rho is a function of height, rather a strong function of height, exponential beta s times rho 0, something rho sea level, let us put that. So, if it is like that, then obviously as you keep on increasing height, then this quantity what you see here keeps on decreasing very fast, okay, and ultimately rho will be so small that your L will be very small. So, then if you see the very first principle that that lift is at least equal to weight or more than weight, so that it can be sustained or taken up in the air, okay, this is W and this is lift. If the lift becomes smaller and smaller, then W becomes larger, and then ultimately what happens, if your lift is very small, W is very high, then this will start coming down actually. Okay. So, you just cannot sustain the lift, that is why state constraints are also important. And if it is very low, what happens is your drag is also a function of that. That means drag is again half rho v square into S into C d this time, and so it is again a strong function of this dynamic pressure. Okay. So, if it is very low, then your rho is very high, obviously you will end up with a lot of drag penalty actually. So, in that is where your I mean our aircrafts typically have something called climb altitude basically, like, so it is not very high, okay, if it is altitude it should be somewhere, I mean somewhere in the there is a kind of optimum altitude within which the aircraft should fly actually, okay. So, then it is alright actually. So, then obviously we need to impose a constraint on the height part of it. Height is a state variable in flight dynamics. So, that is where it is also necessary. Okay. All right. So, let us see the next point. Okay. All right. The next one is, let us say, robotic arms. They are also constrained by physical limits on angular movements actually. So, that is also, I mean, various applications. It is not just aerospace. These first three are aerospace, but even if you go to non-aerospace domain, then also things will pop up naturally actually. Then we can also talk about electrical application, where speed of the electric motor should not increase beyond a limit, okay, to prevent it should not increase beyond a limit to prevent this wear and tear actually. Okay. So, that is also necessity, and also current in the circuit cannot increase beyond a limit, otherwise some components may burn out actually. So, we can list out a variety of applications. I have listed a little from aerospace, little from robotics, and one from something like mechatronics, and or maybe electrical application, and then you have this I mean current circuit applications and things like that. So, in almost all engineering applications, in real life applications, constraint is satisfaction of constraint is a must actually. In fact, in my opinion, constraint is first and then optimization is next actually. So, all right. So, that gives us enough motivation to study this constraint optimal control. But unfortunately, what happens typically is when we talk about constraint optimal control, the solution turns out to be in open loop actually. Okay. So, that is why things are not very much in order, unless there is a typical example problem where you can come up with some sort of a state feedback constraint, I mean state feedback solution and all actually. But in general, the solution nature will turn out to be something like an open loop, which is not a very pleasant thing to see actually. Just keep that in mind. And you can devise algorithms and all that for generic systems, generic nonlinear systems which will satisfy all these things in a state feedback sense is still, I think, in a big way an open problem actually. All right. So, let's so what is the summary of it? The question that you are asking is, can these constraints be explicitly handled in the control design itself? I mean, in other words, one can also think, okay, well, these are the constraints, and I can also have some sort of a penalty function in the cost function which will account for that. Now, that is the usual way of handling that in general also in many practical applications. The reason being, if you can handle that through cost function, let us say the control magnitude is high at some point of time, then you increase the weight associated with the control function. In other words, there is a term, even if you remember our LQR things and all, there is a term something like X transpose QX plus U transpose RU. So, I mean this is the term that we handle actually, right, in the cost function. Okay. 0 to Tf. Now, here if you talk about this as a scalar quantity, or R is a diagonal things and all that, you can talk about something like Q times or Qi times Ui square actually. So, when Ui is approaching to the limit, okay, then you can correspondingly increase Qi, so that it will try to force it down actually. So, that kind of ideas are something called a soft constrained way of handling things, or design tuning way of handling things, but that is not a very neat thing to see. In a mathematically rigorous sense, we should rather handle it as a state, I mean as a control inequality problem straight away actually. So, that is what we are talking about here. So, the question here is, can these constraints be explicitly handled in the control design? And the answer turns out to be yes, you can do it. And the ways to handle is something like a soft constraint problem formulation, which I just now described. And then you can also handle this hard constraint way for problem formulation, which you are interested in mostly. So, the typical way of classification of this problem is in an explicit way is something like this. You can talk about control constraint problems, you can talk about state constraint problems, and we can also talk about mixed state and control constraint problems. So, these three are possible, but largely in these couple of lectures we will give emphasis on control constraint problems and a little bit on state constraint problem. Mixed state and control are kind of mixed algorithms and all that. You can see some references and things like that for your own benefit actually. All right. So, now going back to this a little bit historical development and all that, as I told in one of the classes before, the very first idea of optimal control theory in general probably can be credited to Newton all the way back, where he proposed this steepest descent gradient sort of, steepest descent methods and all that actually. Now, he was not alone, but this is very long ago, about 200 years back. He was not alone. There were great pioneers like Bernoulli, Euler and Lagrange. In fact, we have been talking about EL equation, Euler-Lagrange equations and all that actually. So, these are the contributions from these two pioneers, and there were several others like them. But remember, that was an era where computers were not there and nothing, the computational intensive things were simply pipe dreams actually. It just could not be done. So, but something, it largely remained dormant. A lot of people kind of started ignoring and things like that. But towards the mid 1900s, there was some computers revival, or computers were getting developed, and that was the time where the optimal control got a rebirth as well. So, something happens 200 years later, and these are the pioneers in the 1900s, which almost revolutionized this field actually. Okay, so this Pontryagin, a Russian mathematician, and a Bellman, American, and Kalman is a European person, but then he migrated to US and came back to Zurich right now. He is in Switzerland now. But anyway, so Kalman's contributions are largely into linear systems theory and Kalman filtering in the linear system framework. Bellman, as we know, is Hamilton-Jacobi-Bellman theorem and all that, and dynamic programming. But here is this Pontryagin, a Russian mathematician, who almost single-handedly kind of revolutionized this field in around 1950s. And a little bit on Pontryagin is we will talk here, because that is his ideas that we are talking here, constraint optimal control and all that actually. Okay, so this is S.L. Pontryagin. He was born in 1908 and then he survived until 88, so, and something like he born in Moscow, Russia. But the interesting thing is he lost his eyesight when he was about 14 years old due to some explosion actually. Because of this explosion, even though he lost his lost his eyesight, he continued his exploration in mathematics, and especially was very much keen on optimal control ideas and all that. So, he tried to pursue his passion. Then his mother came to rescue, and then mother helped it helped him in a very big way. In other words, she was writing everything and explaining the symbols and all that. She was not a mathematician, by the way. So, this with that great help, he continued his passion, and he in fact became a very big name in Moscow, in USSR first, then later in the entire world as well. Okay. So, he had lot of this significant contributions in topology, especially in 1930s and 40s. But around late 40s and 50s, he got very much interested in optimal control, and that is where he revolutionized the field actually. Ultimately, he also headed this great institute, mathematical institute in USSR, currently Russia. And he also focused on this theory of singular perturbed systems and singular perturbed systems in ODEs, or ordinary differential equations. And this is what we are talking here, maximum principle in optimal control theory. We are talking everything in the setup of minimization, but when he studied everything on maximization principle actually. So, one other thing, if you want to minimize a cost function, it is equivalent of maximizing the negative part of it actually, the negative of the same cost function. Yes. Now, if you maximize negative j, it is as good as minimizing positive j basically. So, this is what it is, and then in around 1955, that is when he formulated the general time optimal control problem of a difficult problem, fifth order dynamical system describing optimal maneuver of aircraft with bounded control function, and so far that was never done before in a good analytical sense, and people were almost kind of stunned by this development actually. And to invent this new calculus of variation, which was dormant for a while, he spent 3 consecutive sleepless nights as well, and he came up with this idea of Hamiltonian formulation from the for the problem formulation, and that is what we are talking about even in unconstrained domain. I mean in unconstrained problems, first we establish that from the Hamiltonian formulation, and then in this particular lecture we will see how to exploit that for control constraint problems as well actually. So, coming back, he spent 3 consecutive sleepless nights, and then this great idea came to him, and then he proposed this adjoint differential equation methods, these co-state equations and all that, and this is primarily because of this Frontier-Gens development actually, Frontier-Gens contributions rather. Yeah. But as I told, he also contributions, he also contributed towards the singular perturbation theory, as well as later on differential game theory, which we are not talking about, we are not talking anything about that in this particular lecture, course really. But essentially differential game theory is some sort of an extension of optimal control theory, where essentially we have 2 classes of control variables, so one favorable and one kind of unfavorable. Okay. The one tries to minimize the cost function and the other tries to maximize the cost function. You can think of something like a air combat scenario, where somebody wants to attack, the other one tries to kind of get away from that to the maximum possibility. That means one tries to kind of minimize the missed distance, the other tries to kind of maximize the missed distance. So, both are the problem is in relative dynamics. So, both controls play the role actually. So, that kind of problems are called differential game theory, and it has taken a very good impact on the model war games and war game solutions and all that, and especially for air combat scenarios. If somebody is interested, you can see that actually, some literatures around that you can see. There are books available for differential game theory as well actually. And this prestigious Lenin Prize, he and his co-workers were awarded in 1961 actually. So, that's the great Frontier-Gens is one of the heroes of this modern optimal control theory. And lot of this development around optimal control is happening because of his insight into the problem and his way of giving rather simplified solutions, avoiding this EL equation sort of ideas and all that actually. In other words, when you follow this state equation, co-state equation and optimal control equation like that, we do not really talk about Euler-Lagrange equation and all that. We do not even though we can derive these 3 conditions from the EL equation, we really do not worry so much about EL equations anymore actually. Okay. So, that is the contribution from Frontier-Gens. So, let us quickly see a little bit overview of this unconstrained optimal control that we have studied before, and then we will come back to this constrained optimal control actually. So, objective was what we have been studying so far is to find an admissible time history of the control variable from T0 to Tf, which causes the system governed by this nonlinear system dynamics to follow an admissible trajectory, and at the same time it should also minimize or maximize, that means it should also optimize a meaningful performance index of this form, which is typically called Bolzak class of problems, which is fairly very much generic actually. Okay. And also forces the system to satisfy proper boundary conditions. So, all these things we have seen before. Now, to summarize, it has to have it has to minimize or maximize a cost function of this form, it has to satisfy the path constraint, and it has to satisfy the boundary condition as well basically. Now, what we followed is we formulated an augmented cost function of this form, and the dynamics part of it we took it inside the integral. The terminal penalty was still outside, that is J bar, and then we define an Hamiltonian which does not contain any differential terms inside the integration. So, only this part L plus lambda transpose F, and then we define that as Hamiltonian. Then we can continued our analysis for first variation, and the first variation happens to be the first variation of phi, then first variation of entire integral term, but then integral and the integration and this variation, they are commutable. So, the variation went inside, and then we expanded that and carry out this algebra of derivation, and then this term by term we analyzed, and finally we kind of analyze this as well through this this is the term here, okay. This particular term we analyzed in integral sense, and then put some no variation in the initial condition. That condition gives us that variation of x naught is 0, and we continued this analysis, and then finally we combined all these things, all the first variation terms, and then end up with something like that. Then we excited a theorem which tells us that if these equations are true, this equation is true for all sort of possible variations, then the only way it can happen is when the coefficients are 0. And when we invoke that condition, we landed up this state equation, because if you see this part, this cannot be 0. So, this has to be 0, but x dot is del s by del lambda, but lambda if you go, I mean see the definition of lambda, this is what it is. So, del s by del lambda is nothing but f, and then f is I mean what we landed up is same state equation that we started with actually. Then similarly, we landed up this co-state equation from this coefficient being 0. So, this lambda dot is negative of del s by del x. Then we have this optimal control equation coming out of here, okay, and then the boundary condition coming out of here actually. So, this is where we observe that okay, these two equations are compatible. This is a state equation with initial condition, and there is a co-state equation with final condition, and hence it has this split boundary conditions, and then this led to this so called 2-point boundary value problem, and that is what we call as curse of complexity, because of this complex nature of the problem formulation actually. So, not only the boundary conditions are split, but the differential equation nature itself is opposite actually in a way. The state equation is stable, you will end up with co-state equation being unstable, okay, that is a drawback actually. So, these things also we summarize there at that point of time, and we told okay, state and co-state equations are dynamic equations, and if one is stable, the other one turns out to be unstable. And then if the optimal control this particular out of these three equations, optimal control equation is a stationary equation, algebraic equation, whereas these two equations are dynamic equations actually, okay. State equation develops forward because of the boundary condition being given at initial condition, and the co-state equation develops backward. So, this is known as curse of complexity, and traditionally these 2-point boundary value problems demand computationally intensive iterative numerical procedures, which leads to this open loop control structure. All these things we summarized long before, almost at the beginning of the course actually. So, this is what will form the basis of our derivation. Okay, so you can see some of this first variation we made it equal to 0, and that is where we will see how this particular constraint optimal control problem differs from unconstrained problems actually. Alright, so let us start studying that. So, what we are talking now is control constraint problems. Essentially, we are talking Pointryagin minimum principle, and you can also see here that he is blind, his eyes are not there. And the last of largely this material I have taken it from this reference, but I will also list out one or two very early reference, including Pointryagin own reference, which is now available in English as well actually. We will see that towards the end of this lecture basically. So, what is the difference here? Now, the difference is, so what we studied before is something like this. To find an admissible time history of the control variable u of t where t belongs to t naught to t f, which satisfies certain conditions here. So, we did not impose any condition on this u of t at all actually, it was unconstrained, and it can take a very large value if it is so required actually. So, that part we are changing here, okay, and we are telling that the objective remains same for all other things, but there is additional condition out here for the control variable u of t. That means, to find an admissible time history of the control variable in this segment u of t where t belongs to t naught to t f, where the norm of u of t is bounded by certain value, or in component sense each of the component of control variable, that is u j, is bounded between its maximum and minimum value. This is the maximum value of u j and this is the minimum value of u j actually. So, with that condition, that additional condition in action, all other things has to be satisfied actually. Okay, that is a different class of challenge actually. And again let me also admit here that we are not going to follow this very rigorous topological way of dealing things that the way Pantriasin did. What you are going to do is very engineering intuition, and then if somebody is interested in rigorous things in mathematical way, you can always see the reference that I will give at the end actually. Anyway, so little again going back to what we discussed before, what do you mean by variations and all that. And when you talk about variation in control variable, let us say we have a optimum control or optimal control, this thick dotted lines, okay, that is the optimum control that we have already found. But what do you mean by variation? Variation is something that should happen around that actually. That means delta u can be u minus u star. So, what you are talking here is this deviations being this, if you take it together, collect it at all point of time from T naught to T f, there is nothing but the variation actually. Okay. So, this u star is an optimum control path or optimum control trajectory, whereas u of t is something that is close to optimum, it is varying around optimum, okay, but it is not really optimum actually. Okay. So, the idea is if you tell okay something is optimal, that means if I take any variation around that, that is going to give me non-optimal. Okay. So, that is the concept of local optimum things actually. Okay. So, that is the whole thing that we studied before, and this is what we can summarize as well. Okay. That means if u of t minus u star of t magnitude wise it is less than epsilon being a small positive quantity, and then all that it should happen is if I evaluate j at u and then j of u star, then j of u minus j of u star should always be positive 0, I mean greater than or equal to 0, no matter what kind of variation we talk here. Remember u is nothing but u star plus delta u. So, irrespective of whatever is the delta u, then this condition has to be satisfied, then only you get this local minimum. If it happens otherwise, we get a local maximum. And also remember, if epsilon happens to be arbitrarily large, that means there is no bound on epsilon and all that, obviously the solution that you are talking is actually globally optimum. We have discussed all that in one of the early lectures in this course. Now, here is a problem actually. So, what is happening is something like u is okay, u is u star plus delta u. Okay. However, okay, so this delta j I can always interpret as something like j of u minus j of u star. Okay. That has to be greater than or equal to 0, and here remember j u can be a general vector variable sort of thing actually. So, if I write this delta j, which is nothing but the first variation plus higher order terms. So, if I neglect higher order terms, then I will end up with this first variation which is written something like this. So, del j by del u into delta u basically. Okay. However, when norm of u is constrained, that means norm of u is less than or equal to u, the problem, the core issue here is this delta u can no longer be arbitrary actually. Okay. That means we cannot take arbitrary variations around the boundary values actually, and that is where this fundamental philosophy that we assumed in the derivation process while deriving this condition, okay, this particular del s by del u equal to 0, we assume that this can be arbitrary and hence this has to be 0. Now, this is no more arbitrary. So, obviously, we can talk del s by del u equal to 0, and that is the very fundamental drawback of, or rather challenge of this constraint optimal control. So, we cannot tell del s by del u equal to 0. Okay. Now, let us see a little bit pictorially what is happening here. Let us say this is the constraint boundary, okay, and this is what we have already found as something like u star. Now, if I take a perturbation delta u over u star, and then here I have no problem because I can go both ways, here I have no problem, I can go both ways, at least there is some perturbation that is allowed in both ways. But on the boundary, okay, this cannot happen because this perturbation on the top side is not allowed, whereas on the bottom side is still allowed actually. Okay. Alright, so delta j, but remember delta j is 0 varied only if u star lies within the boundary actually. Okay. Here you are just generic j, this delta j we are talking as a function of some generic control variable only. It's not yet tied up with optimal control per se basically. We will see that in a second. So, the problem I repeat, it is it is allowed, both side variations are allowed here, both side variations are allowed here, but here it is not allowed. So, only one side variation is allowed actually, and that is where the coefficient cannot be 0, we have to do something else basically. Right. So, if we but this condition is still there, okay. This has to be satisfied, because if you really talk about u star is the optimal solution, then if you talk variation of delta j around this u star in allowable variation actually, it is not just arbitrary variation, but if you talk about allowable variation, even this bottom part of it and all that actually. Okay. So, even if you take allowable variation, okay, then this delta j with respect to that has to be positive actually, then only we can talk that u star is actually an optimum value, or that is the value which leads to minimization of minimization of j really. Okay. Alright, let us go back to our derivation of unconstrained problems. So, here we had something like this, delta j is given in this big expression, and now we are telling that okay, wait a second, we can actually think of this like this actually. In control constraint problem, variations in co-state can be arbitrary. We are not bothered about co-state variation, we have not put any constraints on that. So, let the co-state be arbitrary, and arbitrary variations can be allowed. That means, we can still talk about this coefficients of that delta lambda, wherever it is appearing, that can be 0 actually. So, that is why we are getting x dot is del s by del lambda, and that is nothing but f of t x u. That means, the state equation we got it back, that is what is also part of the formulation. Okay. Now, if the coefficient if the co-state is also selected in such a way that the coefficient of delta x is 0. Now, delta x may or may not be arbitrary, because delta u is not no more arbitrarily, but remember the lambda is something like a different dimension altogether, okay. It happens in a different space altogether. So, the idea is if the co-state lambda of t is selected in such a way that the coefficient of delta x is 0, okay. We are not telling that delta x is arbitrary and hence it is 0, hence the coefficient is 0, we are not talking like that. What you are telling is the delta lambda is selected in such a way that this equation is valid still. So, then we will end up with the same co-state equation, lambda dot is minus del s by del x. Now, even we can also talk about this boundary conditions are not affected by control constraints, because ultimately the problem objective will be met and all that, and hence the transversality condition still holds good. So, lambda f is still there actually in this form. So, what is left out really? If you talk about this del j bar ultimately, okay, I think a little bit okay, del j bar, then we will end up with only control terms actually, right. Okay, del j bar turns out to be something like this, okay. I think it is also okay. So, delta j bar turns out to be like this. So, what you are telling here is this coefficient is 0, we got the co-state equation. This coefficient is 0, we got the state equation. This coefficient is 0, we got the boundary condition. So, what is left out? Left out is only this one. So, let us keep it actually. Okay. So, this is where del j bar is this quantity actually. Okay. Now, here you cannot tell that the del s by del u is equal to 0, that is not possible. So, what you are telling here is okay, we do not want to talk independently, individually this term and all, but we will talk combinedly. Okay, that means we know that this particular term that we are talking about, okay, I want to see that as it is actually together. And then as you know, we can actually talk something like when delta u is small, you can talk about something like this also actually, right. I mean, this is more appropriate. The second line is more appropriate, the first one is an approximation of that actually, okay, first order sense. So, if delta u is small, you can that these two are equivalent. So, we can still interpret that the entire term is something like this. So, as long as we can make sure that the entire term is greater than or equal to 0, we are done actually. Okay. And here is also a small thing to worry about. Remember u and u star and all that what you are talking, they are not point variables actually, they are also functions of time themselves actually. So, here is the trick that if you are serious to see rigorous things, probably you can see some references or in fact the original work of Enthusiasm. But here imagine something like this actually. Now, assume that this delta u t is arbitrarily small, okay, but this integral value has to be positive. I mean, there is no choice for that. Then only then we can talk about delta j being something like delta j bar has to be greater than equal to 0 actually. Okay. Then only you can say that we have ended up with optimal solution basically. So, if it is arbitrarily small, okay, that means everywhere else, let us say it has gone to 0, okay, everywhere else this variation is everywhere else it is gone to 0, only in this region it has happened some little bit of deviation, let us say something like that. Okay. Everywhere else there is no deviation, that is the variation that we are talking about actually. Okay. So, it is a very small variation sort of thing, and if even in that small variation, if this condition has to happen, then the way it can happen is if the integrand value is positive all the time, okay, irrespective of I mean whatever delta u it is, but we want the integral, I mean the integral value after integration has to be positive. So, it is a path obviously, and what you are telling is if we cannot exclude very small variations, we have to include that also obviously in the allowable sense actually. Okay. So, if that condition has to happen, then this integral will be greater than equal to 0 provided this quantity is greater than equal, I mean is greater than equal to 0. Okay. And that is where we will end up this condition that this Hamiltonian with some control perturbation is greater than equal to the Hamiltonian without control perturbation and the optimal path basically. By the way, in the entire lecture I will not talk about x star, lambda star and all that. Some textbooks including I do will talk about x star, lambda star to denote that those are actually optimal values associated with u star. But just to minimize our notational complexity, I thought I will avoid that. But when you talk about u, that is what primary important here. So, we will talk about when you talk about u, that is non-optimal u, and when is u star, that is optimal u actually. And when is x and lambda, by default they mean that by applying u star I am generating x and lambda, that means it is not just x and lambda anywhere actually. Okay. So, just I thought just keep that in mind, I thought I would put a comment about that. Alright. So, ultimately what you are telling here is if you have this positive quantity satisfied, so alternatively I can take this one in the left hand side and write this equation. That means my Hamiltonian has to be minimized with respect to the u variable. Okay. So, then whatever u it lands up with, that is my optimal control, that is the bottom line actually. So, essentially the necessary condition for control constraint optimal control problems is to find a u star which satisfies this equation, I mean this minimization condition really. So, you have to minimize this Hamiltonian with respect to this constraint space, and then whatever control turns out, it turns out to be optimal control. As remember, all other conditions are already satisfied, state equation satisfied, co-state equation satisfied, boundary condition also satisfied. The only thing that is not satisfied is this del s by del u equal to 0, but the optimal condition is satisfied. Optimal control turns out that instead of making it equal to 0, we have to just do minimization of Hamiltonian within the constraint space. Now, if the constraint space happens to be large enough and this is almost invalid, then obviously this minimization tells us, static minimization condition tells us that the first derivative of the gradient of h with respect to u has to be 0, del s by del u equal to 0. So, that means if it is unconstrained problem, we still use this del s by del u equal to 0, but if it is a constraint problem, we will go ahead and minimize the Hamiltonian within the constraint space actually. So, that is the difference between the two approaches actually. Alright. So, that is what I summarize here. It tells okay, how do you solve a given problem. First, you go ahead and define the very similar Hamiltonian that we defined before, L plus lambda transpose F. Then we still use this state equation, co-state equation and boundary condition as it is, whereas the optimal control equation we change a little bit and tell it has to all that we need to do is to minimize the Hamiltonian h with respect to the constraint control, that means with respect to u, but u has to be constrained within the space that is allowable actually. That means Hamiltonian with respect to u star evaluated with respect to u star has to be less than equal to Hamiltonian evaluated with without u, I mean without u star, any other u basically. Again there is a small notational difficulty here sort of thing. Just to simplify things and all, I have not used x star lambda star in these notations actually. In 90 book you will see this star values everywhere and all that. Some books prefer to follow that, but I thought I will ignore that here. Anyway, so this these are the boundary conditions. This is the procedure. Everything else remains same. Only the optimal control equation takes a little bit different, and that difference results in a huge difference later in the solution part of it. But still, it tells us that okay, del S by del U is not equal to 0. However, the Hamiltonian needs to be minimized with respect to the control variable in the allowable space basically. Okay. And you can now see that this framework what we discussed before in the Hamiltonian method of what Pontryagin gave, state equation, co-state equation, optimal control, boundary condition like that, then constrained optimal control becomes so much easier to handle actually, so much easier to see that what we need to do. Some little bit important observations. Okay, so the optimality condition, this one what we just talked about is valid for both constraint equation and unconstrained equation, I mean both constrained and unconstrained controls problems, whereas this particular equation del S by del U equal to 0 is valid for unconstrained systems only. So, what I mean is again this del S by del U equal to 0, that becomes a special case condition where the control is not really constrained. Okay. Second point is the results given are only necessary conditions. What you see, the sufficiency conditions is a different ball game altogether, and we are not even talking about that. However, if it is an unconstrained problem, then one of the the sufficiency condition turns out to be something like this: del square S by del S square should be positive definite matrix. But if it is a constrained problem, this is not valid. You have to do several other things, and again I am not going to discuss anything here actually. A simple scalar algebraic example just to kind of demonstrate your ideas a little bit clarity sense. So, let us say we have satisfied everything else and landed up with this Hamiltonian with respect to control variable. When I see it turns out to be something like this. Okay. And in general this H, this particular example H can be anything, H need not be Hamiltonian, but let us not lose the focus. So, you can still talk about Hamiltonian is a function something like this, assuming that 6 and 7 this coefficients and this 1 here they are all coming from this after satisfying the other conditions actually. So, our task is to find a particular u which will be satisfying the constraints. The constraint is magnitude of u has to be less than equal to 0, that means the control has to be bounded between -2 and +2 actually. Okay. Then using the relationship between for this unconstrained control, what happens is del S by del U equal to 0. Okay. So, essentially del S by del U is if you do that 2u from here -6 from there, 2u star -6 is 0, that means u star is 3. Unfortunately, this u star equal to 3 is outside this domain. It is not possible to take except this solution. So, we can talk about that as a solution for the variable. Pictorially, this is something like this. If you picture this h of u, that quadratic function, then this takes something like this shape. Okay, in the positive side of it, and then negative. This is the admissible control actually. Okay. So, what turns out to be is obviously this point as a free if you do not put any constraint like unconstrained solution u star is 3, which is something here which is pictorially clear as well, but unfortunately it turns out to be outside this domain. Only this domain is admissible actually. So, what you find out this then all that you tell is okay, within this constraint space that particular value which leads to the minimization of my Hamiltonian. So, this is the Hamiltonian function. So, within the constraint space this is the point where it is minimized. The Hamiltonian value takes a very minimum value at this point of time within the constraint. Then hence u star equal to 2 not 3 basically. Okay. And you can also see that in this case the admissible optimal control u star that can also be obtained through the static optimization results using this KKT condition, that Karus-Kuhn-Tucker condition. If you apply very rigorously, you will ultimately end up with the same value and we have discussed about static optimization problem at the very beginning of this course. You can verify that if you want to. All right. If the constraint has been something like this, rather, let us say norm of u is less than equal to 3, then you are lucky, because u star is 3 is still allowable actually. Okay. But unfortunately, many practical constraints are not large enough to incorporate or to pose the problem as something like an unconstrained problem in general, because the bounds are too far away. But having said that, there are also many problems which will satisfy that, and there are also many problems where you can actually do it in a soft constrained way. That means increase the weighting when control approaches the boundary. That's the method. And once you do that, there are certain nice things that happens to the cost function. Cost function still retains the quadratic nature, for example, and hence convexity and things like that. And also that becomes much more easier to get this state feedback solutions and all that actually. However, also remember that unfortunately many problems will demand that you do somehow explicitly address this issue. Okay, so that we don't run into too much of tuning exercise, and the tuning exercise unfortunately happens to be case by case. That means, if you start from this one particular initial condition, somewhere down the line you may exceed the bound actually. Now, if you increase the weighting at that point of time, if you try with a different initial condition, the value can be high at a different point of time. So, you will be puzzled to where to jack up, where to come down and all that actually. So, those are the difficulties of tuning in that other approach. Whereas, if you just incorporate this hard constraint, the inequality constraint, then that requirement is not there actually. And additional results and all, if the final time Tf is fixed and the Hamiltonian does not depend on time t explicitly, then the Hamiltonian must be constant along the optimal trajectory, and that is true for control constraint problem as well. Okay. If it is a not to control constraint, that is also very much true basically. Yeah. I mean essentially because constraint problems are subset of the unconstrained problems actually. And as a corollary of that, if the final time is free, okay, then what happens if you, I mean this constant becomes 0 as t equal to Tf, typically if you have a quadratic function, things like that. So, there is generalization of that result is if the final time Tf is free and the Hamiltonian does not depend on time t explicitly, then the Hamiltonian must be identically 0 along the optimal trajectory. Okay. So, that is there basically. So, we have proven that in fact before I think probably about lecture number 8 if I remember that. So, this theorem at that point in time talked something like that. Remember, still it is unconstrained problem. I thought I will recapitulate a little bit before going further. So, dH by dt is del h by del t plus all these terms x dot transpose time del h by del x, u dot transpose del u is del h by del u plus lambda dot transpose del h by del lambda. Now, if you combine these two terms using this fact that del h by del lambda is nothing but x dot, and this is a scalar ultimately. So, I can reverse the things. So, then I do that here and then combine these two. Now, what I see here is this term is 0 because optimal control equation is 0. Remember, it is a unconstrained problem. So, that is 0, and this is also 0 because lambda dot is minus del h by del x. So, this term also cancelled off. So, dH by dt essentially turns out to be del h by del t on the optimum path. Okay. And that is the reason, both actually, like if del h by del t, if dH by dt is del h by del t, and then what you are telling here is Hamiltonian is not an explicit function of time, that means del h by del t has to be 0 basically. Okay. So, if the del h by del t is 0, then dH by dt is also 0, and hence the result actually. Okay. So, that is a very simple proof for unconstrained thing. For constrained things, similar things do exist. You can try for arguing out yourself, or you can see some reference actually. So, in conclusions about this particular lecture, just remember that physical systems are always restricted by constraints on control and state variables both. And in this class, we studied about something like a little bit brief summary about constraint or unconstrained optimal control, just to recapitulate the ideas that we talked long time before in one of the early lectures. And then we try to kind of correlate and try to derive this Pointillison's minimum principle in some sort of an intuitive argument actually. and in that actually is a very generic sense what you are talking here. Instead of del h by del u equal to 0, we talk about minimizing the Hamiltonian within the available constraint space. Okay. And also remember that nowadays this static optimization numerical procedures are very strong. That means, even if you put a constraint like that, they are going to solve it very fast actually. So, I mean, I am not telling that it can be solved in real time and all, that is a different ball game. And in fact, this pseudospectral method of solution and all, they are actually in fact talking about it can be handled online also, it can be that fast basically. So, do not get worried that okay, just because it is constraint problems we can't solve it fast and all that, actually it can be done probably. And the next two classes we will study about various application problems and towards the end of the lectures we will talk about state constraint optimal control as well. And these application problems will typically 3 classes, time optimal control including a double integrator problem, then fuel optimal control problem as well as energy integral control problem, and especially in the framework of linear systems actually, because that is where state feedback ideas can be brought in, and then you will see it may result in discontinuous controller, but it will satisfy the bounds actually, that is more important actually. Okay. Alright, so with that comments I will stop it, but before that there are some references as I promised. Most of my material will be taken from this particular book for these 2-3 lectures, DS native, and then I suggest that many of you can actually buy this book. It is a western print and somewhat economy print and all that are available now. Probably you can buy this book as well. Okay. And these are 2 very early references, and this is the Pantyazhin's original work translated in from Russian to English, and it is available in 1962 edition sort of thing. I do not know whether it is really available to buy or it is simply available online free or something, that I have not checked, but you can go back and check it yourself whether it is really available. And also remember the readings will not be in engineering sense. If you are very much math oriented and you have sufficient mathematics background in topology and all that, you can probably think about studying that and understanding that in a good way. And somewhat a simplified treatment is done in this particular book. But this is also not a very recent book. This is also something like published in 66. So, but still I think it in some form or other it may be available over the internet, or maybe some Dover Press or something, they come up with some old classical books in the cheap price versions and all that. So, maybe it is available or not, I do not know, I have not checked it, but you are welcome to check it whether it is available somewhere and you can buy it actually, or you can borrow it, or you can download and print out or something, you can do that actually. Alright, we will study more in the next 2 classes about these problems. But for this particular lecture, I will stop here. Thank you.